All right, guys, we're going to kind of address the last series of trig equations. Give you the technique, kind of show you maybe two techniques that allow us to do this. Um, Tomorrow, kind of tie up any loose ends, kind of show you how to maybe use some of your half angle and double angle formulas as substitutions in some of these problems, which actually kind of ties into what we did yesterday and the day before, using substitutions. But this is solving equations that incorporate like a sine of 2x or 3x or 10x inside the problem, where maybe it doesn't make sense algebraically to use a double angle formula or even a half angle formula. When those avenues are kind of closed down for the problem, this is how you would address them. Okay, they're called multiple angles because that 2x or 3x or 4x, that is a multiple, and x or theta is your angle, right? Okay, and really all it means is if it's 2x, really it means I'm thinking about not only solving for maybe, so let's say it's sine of 2x, and let's say we have sine of 2x equals a half. I'm not 100% only interested in where sine is equal to 1/2 inside one revolution around the unit circle, but because it's a 2x, now I'm really interested in it a second time as well. Does that kind of make sense? So you're trying to rotate around the unit circle multiple times, and that number of times that you rotate is linked to what that coefficient is. So if that was a 3x, we would want to go around our unit circle and find out where the sine is maybe a half within 3 cycles of the unit circle. Okay? So ultimately it should give me 6 solutions. Does that make sense? Okay? A way of thinking about it graphically is to, maybe we start with just a very simple, like sine of x. Let's say here, we know that thing all right, so if I start with this solution, let's just look at this thing between right now. Let's go 0 to 2 pi. Let's just look at one cycle of the sine function. So if I'm interested in where does this thing equal 1/2, I'd be interested in, oh, I did that. Y equals 1/2. There we go. I'd be interested in those two solutions, right? Okay, those two intersection points. But if I change that 1x to 2x, now how many solutions do I have? 4. Okay? And that should make sense. Haven't we talked about how when we take this number here and we make it grow bigger than 1, it is a horizontal compression of our curve. Does that make sense? Okay? So what that's going to do is going to take this curve here, and it's going, when I make that to a 2, it's going to take that curve, and basically I like to think about it this way. It's going to take this, let's make that line blue. It's going to take that blue line, and it's going to push it this direction, okay? And as I push that blue line this direction, let's assume that that red curve is stuck to it. So it's going to take that red curve, and it's going to make it do one cycle between the y-axis and now that blue line. Does that make sense? Okay, so it condenses it. And if it condenses it, so these two solutions right there, okay, are now these two solutions. Does that kind of make sense? Okay. If we make it go to 3, now how many solutions do we have? 6. If I go to 4, how many am I going to have? 8. If I go to 5, how many am I going to have? 10. Okay. You see that in one cycle around the unit circle, you have 2 solutions. So if I go 2 cycles around the unit circle, I'd have 4 solutions, right? Because remember, that's what this this curve is the y values around the unit circle one time, right? Plotted against our radians on the x-axis. So if I go around a second time, this portion of the curve right here from pi to 2 pi is that kind of that second revolution, okay? Or models that second revolution. If we look at it kind of this way, okay? If I'm looking at, let's just say we looked for a sine equals 1/2, okay? It would be at pi over 6, right? And also 5 pi over 6. But if it's a 3x or 3 theta that we're solving for, that would also be a solution, coterminal, right? So that's in the second revolution around the unit circle. And then this would be our third revolution around the circle. Is that okay with everybody? Okay. So that's kind of what the algebra that we're going to go through is going to produce for us, okay? And I think if we just did the algebra and we didn't look at it graphically, some of us would get lost in understanding why certain steps are being conducted, okay? So I wanted to show that to you. And we'll, once we find and do some of this work, we'll go back and show that thing again so we can actually connect to a specific example with specific values. All right, so kind of gave you some instructions here in Technique 1 on how to do this. We essentially solve these things just like we solved things in 7.4 and yesterday in the first half of 7.5. You're going to maybe use your Algebra 1, Algebra 2, college algebra techniques for solving equations, okay? A lot of these end up being multi-step equations. There could be factoring incorporated. There could be, you know, anything that we've addressed so far, maybe even some substitutions that could be incorporated. But you're going to want to pay attention to the fact that you have an argument that says 3 theta there, okay? That's going to tell you that you potentially are going to use this multiple angle technique, okay? So the first thing, if you can't get that 3 theta to be rewritten using maybe identities as 1 theta, you're going to do this process, okay? Basically, right now, and I've got these directions predicated right now off of just this solution, or this question. So because that's a 3, let me put parentheses around this. All right, so it would look like that, right? 2 sine of 3 theta. So what we're going to do is we're going to solve for 3 theta equals my solutions plus 2 pi k. So we're going to try to develop that, highlight it, that type of information there, okay? Which is very easy. We've done a lot of this stuff. It's just the way we write it. Maybe change it a little bit, okay? Then what we're going to do is we're going to divide by 3, okay? So we'll write this out, and we'll divide every one of those spots by 3, because remember what we're trying to solve for is solving for theta, not 3 theta, right? You know, let's say that I had, you know, just maybe a silly equation like this. I've just solved for 3x, not x, right? So if I wanted to solve for x, what would I go through and do? Divide by 3, right? So in this process, what we're going to be doing initially is solving for 3x or 3 theta, and then realize, oh, well, we want theta. So let's divide everything by 3. All right, so that's usually the part that people don't struggle too much with. The next part is where it's not hard, but they forget to do it. It says, then evaluate for k equals 0, 1, and 2, okay? And what this means is that k equals 0, that is that initial rotation on unit circle, okay? The 1 actually corresponds to your second rotation, and that 2 corresponds to actually being the third rotation. Does that make sense? Okay. So really what's going to happen is that we're going to find, I think this one ends up being 1/2. Okay. So on the unit circle, we would have, you know, pi over 6, right? But because we're doing 3 theta, a second rotation would put me there as well. and then a third rotation will put me there as well. So the k equaling 0 is actually for this picture, for that angle, that blue angle. But when k is 1, it would actually be that red angle. Does that make sense? When k is 2, it would be giving us the solutions then for that black angle. Is that doable? Okay. Kind of hard to draw these things and draw and make a link between the drawings and the technique, but that's the process that's going to happen here. All right, so let's just get into the technique, do some problems here, and I think you guys are going to be okay with this process. We have 2 sine of 3 theta is -1 is equal to 0. So again, just like the other ones, okay, regardless of what that 3 theta is, if it's 1 theta, 2 theta, 3 theta, 4 theta, you're going to try to isolate that trig ratio, right, that trig function. So I'm going to add 1 to both sides and divide by 2, correct? So I'd get sine of 3 theta is equal to 1/2. Okay? And just like what we did in 7.4 and what we did yesterday, once we get down to that, once we've isolated our trig ratio, I'm going to ask myself, okay, when is sine equal to 1/2? When does sine equal 1/2? Pi over 6 and 5 pi over 6, right? Well, most of the time when we're doing this, that's a 1 theta, right? So we would have a 1 theta equals pi over 6 and 5 pi over 6, right? But we've just solved now for 3 theta. Okay? Think about this. If 3 theta equals pi over 6, if we just write down that 3 theta equals pi over 6, can I replace that right there? Can I put pi over 6 right there, and would I get 1/2 back? Does that argument make sense? Okay. If I would have left it this way, can I put that if theta equals pi over 6? Well, that would mean then that 3 theta is pi over 2, wouldn't it? Is sine of pi over 2 1/2? No. Okay. So we are asking right now the fact that this 3 theta has got to be pi over 6 to produce this 1/2. Okay. Well, this next step says then divide by whatever that number there was. Okay. So for us it was, actually, I'm sorry. We got to write this plus 2 pi k first. So we'll add 2 pi k to this, because that's going to give me my solutions right now. All my solutions, my infinite solutions, right? Okay. Now what we need to go through is divide everything by 3, because now we're interested in solving for theta. So this is going to produce theta. If I divide everything by 3, divide that by 3, divide that by 3, divide that by 3. Okay? What that's going to end up producing is theta equals, dividing by 3 is same as multiplying by what? 1/3. So pi over 18 plus then what ends up being 2 pi over 3, and I still have my k value. Down here would be 5 pi over 18 plus then 2 pi over 3 times my k value. All right, and I want to talk a little bit about why or what this thing here is actually doing for us, okay, and what that thing is doing for us. When we look at this curve, 2 sine of 3x minus 1 got 3 in there, okay. So when I look at that, what is happening? This pi over 18, let me put put in x equals pi over 18. And what is going on? Two sine 3x. Oh. Let me just kind of start over here. So we had, what was it, 2 sine of 3x. Let's do a times x minus 1, right? Okay, and we were, so a is that, so if I make that 3, okay? So I guess what I was doing in the last one would have been okay. I was looking at 1/2, should have been looking at 0 for my y-axis, for my y-intercept. If I do that right now, guys, the pi over 18 that we just found, let's go pi over 18, comma 0, is that point right there, right? Okay. The 5 pi over 18 that we found is that point right there, correct? Okay. Now, if we're interested in looking at this thing between 0 and 2 pi, we've got some other solutions to find, right? Okay. But they should mimic those two A and B. Does that make sense? If we look in that kind of that second peak there, that second maximum, would you guys agree at that point and that point are very similar to A and B? And I'm going to find what this point here is, C. And I just want to see that if I take the x value of C and subtract from it the x value of A, I want to see what I get. I get 2.09. 2.09. Well, what does that mean? 2.09 is 2 times pi divided by 3, isn't it? Sometimes I hate this thing. 2 pi divided by 3 is my 2.09. And that 2 pi over 3, was that algebraically generated right here? Does that make sense? Now, if I let this k kind of be kind of what we call an index, okay, which is allowing me to basically say, okay, when k is 1, that's going to produce that point C. When k is 2, it's going to produce that point D. Okay, so if I take ultimately A, the x value of A, add to it 2 times 2 pi over 3, so that's k being 2 right there, okay, and then comma 0 should put a point right there on D, and it did, okay, and it labeled it E, so you can't really see separate them, okay. Does that kind of make sense to everybody? So the algebra that we're going through is allowing us to generate those additional solutions that we create when we take the sine function and we condense it with that coefficient of x or theta or whatever variable we're using. Okay. So now this is giving me all my solutions. This is my initial one. Okay. Pi over 18 is my initial one. But I also got, remember, I want to go between 0 and 2 pi as final answers. And we're seeing, like I said in this picture, 2 pi is right there, correct? So the initial ones were there. We got to work to find these other 4. And that work is done by letting k equals 0, 1, and 2. K equals 0, 1, and 2 there. And the 0, 1, and 2, like I said, this pi over 18, that is when you are in your first rotation around the unit circle. Okay? When I go pi over 18 plus 2 pi over 3, that is ultimately producing the 1/2 in a second rotation around the unit circle. Does that make sense? And when it's 2, that is that third rotation around the unit circle. Or if we think about it graphically, okay, breaking up. So that is k equals 0, okay? This would be k equaling 1, okay, starting that second revolution. And this would be k equals 3, starting that third revolution. Does that make sense? Okay. So then we just go to the side and say, okay, this thing here is going to produce, when k equals 0, theta equals pi over 18. When k equals 1, okay. Now, doing this work here, I'm going to be adding fractions, right? What is the necessity that we need when we, the necessary feature that we need for adding fractions? Common denominator. Doesn't it make sense then? Instead of having to find that, instead of multiplying this thing here and making like 4 pi over 3 and then, 2 pi over 3, and especially when k gets to be a larger value, I don't want to really find that common denominator every single individual time. Doesn't it make sense at this stage here to make a common denominator here? Does that kind of make sense? So we'll make that 12 pi over 18. It's still 2 pi over 3. Same thing down here in this one. Because now, when k is 0, obviously that goes away. It's using pi over 18. But when k is 1, this is going to be a 12 pi plus 1 pi, right? So my numerator becomes 13 pi. And my denominator will be 18. And when k is 2, theta will be, add another 12 pi over 18. Gives me, what, 25 pi over 18? And that's just taking 2 and plugging it in right there, getting 24 pi over 18, and then adding pi over 18 to that. Okay? Another pattern you might be able to see, and it's the same exact work, but maybe from a different perspective. What's the difference between those two solutions? 12 pi over 18. This works because this thing is being multiplied by k. There's a kind of a direct variation kind of occurring here between these solutions. What's the difference between those two? 12 pi over 18. So if I find the first one, and I know that basically that common difference, I can keep adding that common difference to find my others, right? Does that make sense? Knowing that I should only have 3, okay? Because the 3 theta. Does that make sense? All right, so now I gotta go find the same thing, do the same work with starting at the 5 pi over 18 one. So if k is equal to 0, theta obviously would be 5 pi over 18. If k is equal to 1, okay, up here we added 12 pi over 18, and we're going to do the same thing down here. Add 12 pi over 18 to this, and you get 17 pi over 18. Add 12 pi over 18 to that, and you get 29 pi over 18. And those then, guys, are your solutions. Those are solutions on the interval 0 to 2 pi. Okay? Those are your 6 solutions that are developed when you take that sine function and you ultimately condense that curve. Okay? You squeeze that horizontal compression. Okay? Now, how do I find the solutions outside of 2 pi? Let's think about this. If I go outside of 2 pi, so let's look at just taking this restriction off. Maybe I go out to, I don't know, let's just go 12 pi. Okay. How do I find those other solutions out there? Well, let's take A. Let's take the x value of A. And what do you think I'm going to add to that x value of A to get that point right there? 2 pi again, right? Does that make sense? And what am I going to add to B to get this point right here? 2 pi, okay? So if I've got these 6 solutions, x equals 2 pi. If I got those 6 solutions between the y-axis and that line of x equals 2 pi, okay, ultimately adding 2 pi to that one is going to give me that one. Adding 2 pi to that one is going to give me that one, right? And then the same thing happens for the rest of them. So if I want the infinite solutions, that just means take each one of these and add 2 pi k to them. Okay? Now, that can be kind of a pain in the butt to write. On the test on Friday, if you want to write it this way, remember yesterday we said solutions. I'm going to say theta is equal to the curly brace means solutions. I'm going to write a parenthesis, pi over 18, 13 pi over 18, 25 pi over 18. There's really no way around writing all of these out. I will give you this. We take those 6 and then just say we're going to add 2 pi k to all 6 of them, such that k is a, what's that z mean? Integer. You want to rhyme that way, that's fine. I think, you know, the higher level math class that you get into, that would be probably one of the preferred methods of writing your answers. If you guys on Friday, if you come up with that list of that we have there in green and red and blue, and then you just want to circle them and say plus 2 pi k, all of them, that's fine. I'm okay with that. Just be leery. I mean, ask those questions. When you get to another math class, you get to a science class, ask those questions about how you're going to be grading on your notation. I think notation is a huge aspect of courses, but you know, I'm not going to make you, or I'm not going to grade you that, I guess, detail on it. Is that okay? Can we do that? WebAssign, I believe they want you to type in pi over 18 plus 2 pi k, comma, 13 pi over 18 plus 2 pi k, comma, 25 pi over 18 plus 2 pi k. Okay? Use your cut and paste tools to maybe do that a little bit quicker. All right? Can we do that? So that's one technique. Another technique, kind of at a crossroads of whether I show this or not. I showed it in the last period, so I'll go ahead and show this with you guys as well. But it is the same thing. It's just kind of viewing it maybe from a different perspective. We're going to do it with the same equation. So you know, if I start with 2 sine 3 theta minus 1 is equal to 0, go through the same algebra. Eventually, it's going to get me sine of 3 theta is equal to a half. Okay, but here's where maybe we look at it from a different perspective. Initially, the solutions say we want to be on the interval from 0 to 2 pi. Okay, but because that thing there is a 3 theta, what I'm going to do is I'm going to multiply this by 3, and that tells me to look at the interval from 0 to 6 pi. Okay, I actually think this process is actually a little bit easier to use than technique 1 when that 3 is a fraction. Okay, we'll talk about maybe some of those tomorrow. All right, so now it says find all solutions from 4 3 theta from 0 to 6 pi. So we're going to be asking a question, okay, when does 3 theta, okay, when does sine of 3 theta equal 1/2 from 0 to 6 pi? So from in the first revolution from 0, basically what we're doing is say, okay, 0 to 6 pi, is that 0 to 2 pi? I don't know if you would ever write it this way. Union 2 pi to 4 pi. Union 4 pi to 6 pi. Is that going to make sense? 0 to 6 pi, the union of those 3 kind of rotations. Okay? So what I want to do first is basically think about, okay, where is sine 1/2 in between 0 and 2 pi? Well, we've already done that, right? We said it was pi over 6 and 5 pi over 6, correct? Okay. The next thing I want to do is say, okay, where is sine 1/2 in between 2 pi and 4 pi? Well, that's at the same spots. It's still there and there on my unit circle, right? But now instead of 1 revolution, it's now that second revolution. So my starting point would have been 2 pi, and then up pi over 6. Does that make sense? So what's 2 pi plus pi over 6? 13 pi over 6. Okay? And then this one here, the second one over here, this point, it's still coterminal with 5 pi over 6, right? So add 2 pi to that, and you get 17 pi over 6. So those two solutions are coming out of that interval, ultimately the second rotation around the unit circle. The third one would be between 4 pi and 6 pi. So now I'm looking at this number here being that point. But now how do I get back to it after one more revolution? I add 2 pi to it. It gives me 25 pi over 6. And this would give me 29 pi over 6, right? Now, if you look at these numbers, you look at those numerators for those 6 fractions, are those the exact same numerators that we had in the first technique? We had a 1, a 5, a 13, 17, 25, and 29, right? But what were all the denominators? 18. How do I get those denominators? Yeah, I got to divide everything by 3 here. And I'm going to, instead of divide by 3, because I think it's easier, multiply everything by a third. So multiply the left-hand side by a third, and that's going to give me theta for all of these. Okay. And then I multiply the right-hand sides by, multiply both these by a third, so give me pi over 18, 5 pi over 18. This one's going to give me 13 pi over 18 and 17 pi over 18. And then this one, 25 and 29 pi over 18. And are those the same 6 solutions? It's just kind of looking at it in a different perspective. And what happens there, okay, so initially we kind of increased our period, right? Increased our domain that we're looking at, okay? And that gave me the idea to look in basically 3 revolutions. These solutions then, when I divided this by 3 then, the 3 theta, I'm ultimately dividing that again by 3, and it gets me back to 0 to 2 pi. So what that tells me then is that these 6 solutions, all of them are between 0 and 2 pi. Okay? I don't think that's, that's the way I learned it. But I don't think that that's the best way to do it. I think the most direct way is to use technique 1, but I'm going to leave it up to you, whichever technique you feel comfortable with. I'm going to, in class, when we do some more examples here, I'm going to use technique 1. Okay, I just feel more comfortable with that, at least in explaining it. Let's do... These other examples I have on here we'll address maybe tomorrow, but I want to do a different equation than what I've got written in there. So let's take an example. I think last class we did secant of 4 theta minus 2 is equal to 0. Secant of 4 theta minus 2 is equal to 0. So obviously here, probably not going to make any double angle substitutions here. We could, because it is a multiple of 4 theta is a multiple of 2, right? So double angles could work here, but it's probably going to get kind of messy, kind of ugly. This process is much more efficient. So we just solve for the secant of 4 theta. So again, not a hard algebra problem, and we get that. Okay. Now here's kind of the issue of the unit circle. If I go on my unit circle, all of the points that we've learned off the unit circle are a cosine comma sine, aren't they? You probably haven't maybe necessarily memorized directly. You do know them, but you haven't directly memorized what the secant values off the unit circle are. Okay? So would I want to deal with it this way? No. Can I do anything I want to an equation as long as I do it to both sides? Okay? And maybe even we write it this way. If I write that as a fraction, both sides, what do we have? What do we call an equation in which you have two ratios that are equal? A proportion. And one of our properties about proportions is that the reciprocal of your proportion should still be true. So could I write this as 1 over secant of 4 theta equals 1 over 2? That makes sense? What's 1 over secant same as? Cosine. That makes it a little bit easier to deal with this problem. Okay? Now, I don't think a lot of people are probably going to write that stuff down, but I wanted to give you the logic of why we can do this. Okay? If you're ever given secant of something is equal to a number, okay, don't ever deal with the secant. Deal with the cosine of that reciprocal. Okay? For the same reason, if I ever given cosecant, and I've solved it, said cosecant of something is equal to something, I'm not going to deal with cosecant. I'm going to deal with sine. Okay? So just take reciprocals, and it makes things a little bit easier, because that's what the unit circle is in terms of. All right, so let's talk about when is cosine equal to a half? Pi over 3. And pi over 3. Okay. Hopefully that's something that we know, right? Okay, hopefully that's something that we can replicate on Friday. I'm not giving you the unit circle. Okay. It's kind of disconcerting when I ask a question, cosine 1/2, and it's crickets. Okay, or it's the same person. It's been answering the same questions for an entire 3 weeks. Okay. Hopefully we all know those. Okay. So 4 theta equals pi over 3. Now remember we have to add. Well, I was going to add the 2 pi k. Add the 2 pi k. Okay. And now this is the situation where we then divide everything by 4 to solve for theta. And dividing by 4 simply is multiplying by 1/4. So I'll write that as pi over 12. Now this becomes just pi over 2, right? Can I write pi over 2 as 6 pi over 12? Just to save a little bit of time. That's why I'm doing that, is because I want to add these two things together, so I want that common denominator. Still going to have k there. And then here, it's going to be 5 pi over 12 plus then 6 pi over 12. Once you kind of develop that process here, it's just mimicking it down here. Okay, so I didn't really do any algebra down here. I just followed what I did up here. So then we're going to let our k value go between 0. That's where you always start with. You then go to 1. How far am I going to go? I need as many k values, starting at 0, I need as many k values as I have multiples of my angle. Okay? So I'm always going to, if I start at 0 then, I'm always going to go up to whatever that number is. A lot of times we call that number n. Okay, so I start at 0 and I go up to n minus 1. Okay? And we do the same thing down here. 0, 1, 2, 3. So then with this solution, if k is 0, okay, if k is 0, I'm going to have pi over 12, right? If k is equal to 1, I would have 7 pi over 12. Just adding these two things together then. And if k is 2, then you're going to have 12 pi plus pi, which is 13 pi over 12. And if k is 3, you're going to have 19 pi over 12, right? Again, you can see the pattern that the common difference between successive solutions is 6 pi, right, over 12. So once I find those two, and that's a pattern you can always use. Once I find the first two, I know the next ones, as far as I need to go. But you need to know how many Ks you're going to use so you know when to stop that pattern. So down here, if I start with 5 pi over 12, 5 pi over 12, I will add 6 pi to that over 12. Add 6 pi to that, so 17 pi over 12. And then add 6 pi to that, 23 pi over 12. And now I stop because I knew that k was going to provide me 4 solutions. So this was when k was 0, k was 1, k was 2, k was 3. And those are my set of solutions between 0 and 2 pi. Okay? So let's see what this means to us graphically. Okay, so if we look at secant of 4x minus 2, original equation, equal to 0, so I'm looking at these x-intercepts, okay? See if we can produce these x-intercepts by using the information that we came up with, okay? So I'm going to try to do this quickly. So let's say that we have an ordered pair. The first ordered pair was pi over 12, right? Pi over 12, and then it was plus, what do we have? It was a 2, yeah, 6 pi over 12, so pi over 2 times k, and then I'll put comma 0. So that should give me a point. It's based off of k being some value. So right now, let's take this k and make it an integer. All right, so if k is 1, or sorry, if k is 0, that gives us that solution right there, 0.26, where if we were to take pi divided by 12, there's your 0.26, okay? Now, if I make k go to 1, it gives me that solution there, right? Okay, so then that is, let's put the value in these. So 1.83, okay? So that would be the, what is that, 7 pi divided by 12 solution, 1.83. And if k goes to 2, okay, so that should be the what, 13 pi? And then if k is 3, it gives me that one, right? Okay. Now if k is 4, it goes off the graph, correct? It's outside the region from 0 to 2 pi now. So those gave me those solutions, or that gave me that set of solutions. Let's start with the 5 pi over 12 plus then pi over 2 times k, comma 0. Let's see what those solutions look like. Let's make that point blue. And if we look at the ordered pairs there, When K is 0, we get that red point and that blue point. When K is 1, we get that red point and blue point. It's 2, we get those 2. And when it's 3, we get those 2. Does that make sense? All right. What I like about using GeoGebra is before I go through and kind of waste my time in finding these 8 individual solutions, I can use GeoGebra. Now, you got to take a little bit of work to practice with it and understand how to write those equations, basically those varying equations that we typed in right here. Okay? But it's not that difficult if you've been watching for about the last 3 months. I've been doing that kind of stuff. You can check to make sure that this is true. This works. And then go find the individual ones. Okay? If I wanted the infinite ones, one of the infinite solutions, we're going to take all those and add 2 pi k to them. And we'll take all those and add 2 pi k to them because the secant function has the same period as its reciprocal cosine function. Okay? If it was the tangent or the cotangent, what would you be adding? Just pi k. Right? And that would be the same thing, you know, when I had 4 theta is equal to pi over 3 plus 2 pi k. If I was dealing with tangent, it would be pi over 3 plus just pi k. Is that right? So whenever you're using 2 pi k at any stage, if it changes the tangent or cotangent, in its place becomes pi k. That 7-5 assignment, towards the end of it, you're going to see some questions like this. Tomorrow, I want to go through and go through a few more of these, but also give you insight on a few questions I'm not going to ask you about on Friday. You're not going to see in your homework, but I want you to maybe be able to address them, at least see how we can deal with them. Thank you, too. Cheers.